Okay, so it's good to see that some of you are interested in using Java 8 because I will assume a certain level of Lambda knowledge, but I will go through it in a bit of detail. Now, my name is Peter Lawrey. I have a small consultancy based in the UK. There's about 6 of us dotted around different parts of the world. Our clients are largely in the UK, Europe and the US, but we have the occasional client in other places such as Melbourne. And I'm originally from Melbourne, grew up in Eltham. I've done a few things on the internet. You might see me on Stack Overflow. I have more answers than anyone else in Java and the JVM. I'm the founder of the Performance Java Users Group, which has got nearly 1,500 members now. I've recently been voted a Java champion, and something else I was going to mention, doesn't matter. Yeah, so we worked on a project recently to migrate a C# project to Java, and it made sense to use Java 8 since C# was written using the equivalent of streams. And so we migrated. We have a 25,000 line application that's been in production for a few months now, which has given us a bit of knowledge and learning experience from having actually used Lambda code, and in particular worked on Lambda code that's been around for a few years, like even before Java 8 existed. One of the reasons that was quite useful in Java 8 is that there were 4 different standards that were proposed for how Lambda should be implemented in Java, and in the end they basically picked the standard that was closest to C#. And in fact, one of the most obvious differences is that in C# it's equals greater than, whereas in Java it's minus greater than, yeah, for a Lambda. I'm guessing they figured that equals greater than could be confused with greater than equals. Okay, now one of my initial reactions to lambdas was that there seemed to be a pretty complicated way of doing something simple. And a lot of this reaction came from the fact that most of the examples were pretty trivial. So they're easy to explain in an example, easy to show how the transformation would work, and most of the time seem to be simpler in using a plain loop than trying to use a stream. And it was only when I started to work with these that you start to see examples where actually it was a lot nicer to use lambdas than to try and do the same thing in loops. When we did the migration from C# to Java, in reality only about 10% of the code was written using lambdas. So not all the code was lambdaized or streamed. But for the cases where it was used, it was really valuable. Another thing that was important was that the use of parallel. So there's a lot of concern about that parallel streams will be overused because it's very easy to switch a stream to a parallel stream, and this can cause all sorts of performance problems because you're basically overutilizing a limited resource, which is the common fork join pool. The nice thing about it is not that it's easy to add parallel stream, it's very easy to reverse it. And what I've seen many times is people will write parallel code and they've gone to a huge amount of effort to write it, a huge amount of effort to test it. And even if it doesn't really prove to be a lot faster, they haven't really allowed a lot of time to go through and then reverse all those changes to pull it all out again. So you end up seeing cases go into production where something's been written in parallel when it was never really proven that it helped. And in many cases, a lot of consulting places where they haven't got a handle on the performance and they've got no control over it, is you pull out as many threads as possible. For one client, we reduced, they have 5,600 core threads and 100 supporting threads. We reduced the 5,600 to 1, and in that process we improved the performance by a factor of 10. So, and they've now recently considered going to 2 threads to improve. So sometimes with threading, less is more, and the nicest thing about parallel stream is that you can switch it back to stream. You've invested very little in making that happen, and then pulling it out again is no shame. And in fact, what we did when we went through and optimized this code. Like I said, about 10% was streams, which is about still 2,500 lines of code. In reality, we used parallel streaming 4 places in the end. That was enough to use all the resources of the machine. It didn't make sense to use any more. Okay, so the key thing in low latency in Java is garbage. How much garbage do these things produce? And so an important target is trying to reduce your garbage rates far lower than most Java applications would worry about. Now, for a web application and most server applications where throughput is important, not latency, you will get about 95% of the benefit by cutting your garbage rate to about 400 megabytes a second. In most cases, once you get to about 300 megabytes a second. Once you get to about 300 megabytes a second, you start to get diminishing returns in terms of throughput. But in terms of latency, you want to go much, much further. And certainly for high-frequency trading systems where low latency is critical, you may be looking at garbage rates of a gigabyte an hour, if not, in the extreme cases, a gigabyte a day. Right? Now, the benefit of going to a gigabyte an hour is that you can create a large Eden space and run an entire day without a single collection. That's not just no major collections, no minor collections either. So now GC pauses are no longer an issue. Very simple and elegant way of eliminating GC pauses as an issue in your system. So there's a lot of focus on, well, how much garbage do these operations perform? And at first glance, lambdas look really bad because they have notionally objects all over the place. So we'll look at that. And what can you do to tune the use of lambdas? So just looking at some interesting examples of using the streams. This one is actually of optional, and it's a replacement for an equals method. And the reason this is interesting is that this uses optional in a much more complex way than most examples you might see. So what we do is we create an optional which might be nullable, so the equals object itself might refer to null. And then we filter it. So instead of doing an if condition that says, if it's not this instance, return false, we just apply a filter. Then we apply a mapping so we can change the type, which is equivalent of the cast. Then we say filter where the first entry is equal, the first field is equal. Then the second field is equal. And finally, we decide whether this is still, we are still dealing with an object. Has any of these previous restrictions resulted in nothing? And this is one way of creating an equals method. The reason this is interesting is that effectively, optional here is a stream of 0 or 1 values. That's all it really is. So it's still a container, but it has a lot of the manipulation options that you would expect to see on a stream. Any questions about this?
Can you remind me what that means?
Here, okay. So what happens is you've got a lambda here, and a lambda is a bit like an anonymous inner class. What you would have in an anonymous inner class is you would have to define an argument of a particular type. But in Java 8, it uses type inference. So with type inference, something that Java 7 did not have, really, is that it can work out the types. It knows what the type has to be for this to compile. Filter will only take a predicate. Filter will only take a predicate that takes an object and it must return a Boolean. So if you look at the interface for predicate, it's just a simple interface that has one method. That one method takes an object, and which is called test, is the name of the method, and it returns a Boolean. So it knows that this must be an object, and this expression must be a Boolean. And so, and this object must match the type of this, which is actually just object in this case. But if this equals for something else, it would infer the type all the way through. So that is the only bit that you need to provide. You don't need to provide the types anymore. You don't need to provide the method name. You don't even have to know that this is a predicate. All you need to do is provide the name of the variable you want to use, which is here. And in fact, what I do is if I don't want to specify, sometimes you have to provide a variable name even though you have no intent of using it. And so what I'll do is I'll put dollars here. For whatever reason, they've decided the underscore is no good as a variable name for a lambda, which makes sense, I guess. But they've decided that dollars is still okay as a variable name, or any other currency for that matter. So if you want to use Greek, drachma, all the currency symbols are fair game, because you don't want to discriminate one currency against another, of course. So what's happening here is it's creating a field. So where does it get a bit? None of these are particularly interesting in terms of types because we started with an object, but essentially what this equals does, which is different, is that either of these can be null, and this will only return true if both of them are null, or both of them are the same object, or both of them are dot equal to each other. It handles all the null checks for you, basically, which you would normally have to have written, laid out in your equals method.
But you're kind of doing what object equals is kind of doing anyway, just showing that out in one form.
Yes. Yeah, it's for a type that has two fields, S1 and S2, and for this code you don't even need to know what S1 and S2 actually are, because it's just comparing the object types, values. But so this is defining your own equals method, but using optional to do it. And the reason I'm showing you this is because most examples of optional are really trivial. You just return an optional. There's methods that return an optional, and then the first thing you do is grab its value out. And in fact, there's an easy way to pretend optional doesn't even exist by doing dot or else null. And then it will return a type that can be null if it's not present. So you can sort of go back to coding the way you've always done things. Try and avoid doing that, by the way. But it may be that you're passing this through to an API that expects, Java 7 behavior. So there may be no choice. But
and does optional not take a generic type?
it can do. So for example, it will implicitly work out what the type of this is, which is an object, and it will have this type. It is a generic. So you can end up putting in angle brackets in here, what type you actually want it to be. It has to be a super type of what you're passing in. I can't think of a good reason why you would do that, but there are cases, for example, and in fact in the next example, where type inference fails and you end up having to specify the type. Maybe future versions of Java 8 won't do this, but
So it's simply the instance of just starts bringing alarm bells, so instance of anywhere.
yes, and that's because of the way equals works, is that it implicitly has to work off an object. I think in C#, for example, you don't need to do that. It works that out for you. So you do equals, and you're given an actual concrete type, which it must be equal to, and it assumes false if there is no matching equals method, which is somewhat pragmatic choice, but it certainly gets rid of quite a bit of boilerplate. It's also a bit of a gotcha if people convert from C# to Java, because they write code like that, it all compiles, it just doesn't work, because it doesn't call that method.
So all these methods we're seeing here of nullable, filter, map is present. They're all on optional.
Correct.
And what are they returning?
Okay, so in this case, this is a factory method for an optional. This one is a filter, which just returns another optional, which can be null if this test fails. And then map will return another optional, which will never fail, but now that the type has changed, so this is an optional of object. This one will return an optional of test. Again, this filter just applied again, so it could return an empty optional, or one that's not present, or another, or the same object. again here, and then finally you've got the isPresent test.
So they're written in a fluid manner. They're each of those are returning optional back again.
Yes.
But they're essentially wrapping around some value that we're going to test with that end call to isPresent.
Correct, and it's important that you consider that, because in reality, this is just building up an expression. So if you don't put this in here, nothing will happen in reality, right? This code won't do anything at all. It kind of is a bit obvious, but there is ways to actually see what's happening before you even do this terminating method. But in all cases, streams and optional, you have to have a terminating method. Otherwise, it will deduce that this expression does nothing at all and won't run anything. So if you've got any parts of this that have side effects, like you expect equals to be called, for example, you've got some debug statement in there, it's your method. This will not be called if this is not called, because it just says, oh, well, you don't seem to be doing anything. It won't even bother starting the whole process.
That wouldn't compile it.
Sorry?
You don't put that isPresent in there.
It won't compile because it won't return a Boolean. But yes, so say, for example, return, this is a void and return wasn't there, nothing would actually happen.
What about if you omit the isPresent and instead of that say optional dot rest of the thing and then equals null?
Yes, you can also test to see whether you can do a dot or else null dot get equals null.
I mean, instead of isPresent,
Mm-hmm.
replace it with equals null.
Well, the optional will always be not null, but you can get to the value in the optional and test whether that's null. And in reality, if it's not present, then in fact the value is null. They're the one and the same. If the value is null, it's considered not present.
One more basic question on this sort of succession of calls. You mentioned side effect. I've heard that a couple of times. What exactly does that mean in this context?
Okay, so say for example you've got your own equals method that's not using object equals, and in there it prints to the screen what you're comparing and saying whether it was the same or not. So that will only actually be called if isPresent is there. It doesn't evaluate each of these expressions, work out what the result is, and then finally realize that throw away the result. In fact, it does them lazily. It doesn't really do anything with any of them until it hits a terminating method, decides what needs to be done. Which means, like I said, if you've got some sort of side effect. Now, the most common side effect, somewhat of a deliberate side effect, is .peak. There's a method called peak, which allows you to see what the value is at any given point. It's sort of used for debugging purposes and some other non-ideal purposes. So in particular in stream, if you want to see at a particular point in the stream what is happening, you can put .peak system.out println, right? So you can just see at a given point, as sort of like a debugging point, what's happening in your stream.
So because with
But
each
that's
of
the
those
side.
calls, we're passing it in a Lambda, which is a piece of code that it will run,
Yes.
and it's essentially going to maintain an array or a list or something of all those Lambdas, and only once it hits that terminating one, then it will start going through.
Actually doing anything with it. Yes, yeah, and it's called a pipeline under the bonnet, but yes.
It's called what?
A pipeline. Sorry, yes.
You said that you could do .peak for debug. Is there an easier way to debug?
You can step through them, and one of the other things they added in Java 8 as opposed to Java 7 is that in Java 7, when you have a stack trace or a debug, the very first line is the line that all of this exists on. In Java 8, it actually treats each one of these as a separate line. So if you get a stack trace that's thrown on this line, it'll actually show you this line, not the top one. And in fact, when you debug it, if you debug in and out of the library, it will come back to this line. The tools, in my opinion, the tools aren't quite ready. I mean, it works, but it's obtuse in the sense you see yourself going in and out of the library code, which can be quite confusing. The other thing that's confusing is that the scope changes. So because you're in a nested method at this point, you can't see anything outside it. So if you're at debugging at this point, you can't see what object is, right? If this was equals code or loop code instead of streams, you would be able to see every variable in the method that's in scope. But in fact, here you can only see every variable this Lambda uses, which is slightly confusing. You have to sort of wind back up the stack to find the pointer which matches the equals method. Then you can see the scope, what's in equals. Now, I think in time the tool set will sort of catch up, and it will it will hide some of those details from you. Okay, lots of good questions from that slide. So, I'll give you a more complex example. So, this code in sort of a one-liner, not really a one-liner, will find the 20 most frequent words in a file. And the nice thing about it is that whether you make this parallel or not parallel is whether this dot parallel is added. So you don't need to change this code anywhere else to make it parallelized. And that's one of the cool things about parallel, and why some experts believe it will probably be overused, because it's too easy to just add it in, right? So what does this do? It starts by, on this line, it starts by turning every line in a file that comes from a path into a stream. Now this stream is lazy, so you're only dealing with one or a few lines at a time, so it's much more efficient than, say, reading it into a list and then going through the list, which is what the Java 7 implementation did. And then it splits it up. Now, with dot parallel, it can actually start breaking up these lines and divvying them up to different threads. Now, one of the implementation details is there's a fork join pool. Can't remember the class it sits in at the moment, but there's a fork join pool which you can access, and it has one less thread than the number of threads in your machine. The reason is that it will use the current thread as part of its workforce. So if you've got 4 CPUs in your machine, the pool will only have 3, and it will give a quarter of the work to the current thread as well as the 3 additional threads. So it's one of the details that you see when you run this. So it's done a lot of the work for you in terms of dividing up this work, putting it across multiple threads, and doing all the synchronization and merging. So already trying to do that in a loop, it's starting to get quite difficult. All right, so what does this line do? It takes each line, breaks it up into words, which is what the /b does, and then gives you back a stream. So you've now got a stream. For every line, you've got a stream of lines. But now we've got a stream of streams of strings, which is not really what we want. We just want a stream of strings. How do we deal with that? Well, instead of using map, which would do that, we use what's called flat map. The difference between map and flat map is that flat map expects to take streams of have a stream of streams, and it just concatenates them all together. So what comes out of this is actually just a stream of words, which is quite elegant. Now the next step, what it does is it takes those stream of words and starts grouping them together. Now in most cases where you do a group by, it's like a group by in an SQL query. You give it a key and it will create a map which has all the elements which have that key. So my common output is something like a multi-map, and in fact that's the default behavior. So say you've got lots of people and you want to group them by first name, right? You'll end up with a map where the key is all the first names, and then all the values are lists of all the people which have the same first name. So this is a common use case for group by. Again, doing a group by in a one-liner in Java 7 is quite difficult. However, this is a slightly different group by. What I'm doing here is that the key is in fact the entire word itself. I want to group all of the words together that are the same, but I don't want to keep them all. I don't want a list of all these words. I just want to know how many there were. So this is what this counting method does. It takes, instead of accumulating a list of these words, it just accumulates a number. And then finally, so now we've got a map of words and their frequency count. But we want the top 20. So I take this map, get the entry set, and I turn it into a stream and I start sorting them. And at the moment, this is where type inference finally fails. It cannot work out what the type of this entry is. I'm not sure why, because 2 lines later it can work out the type. But anyway, so it says, I want to sort all the entries by their value, which is the count, in reverse order. Right? So I'm now starting from the top, most frequent, highest number of occurring to least. And then I use this nice little method called limit. So you can limit how many you want to get. In this case, I want a limit of 20, so I get the top 20. And but I've still got all the entries. I've got all the entries for the top 20 words. And you can get some really impressively dense code out of it. That's right.
With that collect method, is there any ordering guaranteed between the streams when it concatenates them together?
No. And in fact, it's concurrent, and there is another grouping by, which is grouping by concurrent, which would actually be slightly more efficient in this case. Sorry.
You can put is that the dot ordered on the, like set the ordered property behind the scenes on this on the stream. Then I mean I don't know, performance would probably go be really terrible.
Yeah. Yes. In C# you've got a lot more guarantees as to the order in which processing occurs, but in Java they tend not to. So, for example, this grouping by, it actually puts them into a hash map, whereas in C# it puts into a dictionary, which is closer to linked hash maps. The order in which they're added actually matters, whereas here the hash map it creates isn't ordered. So you may find that actually, if you want a particular ordering like this sorted, you have to be explicit about it, because it may not work. And this is one of the problems we found shifting from C# to Java, is that were implied ordering guarantees in C# that didn't apply in Java in what looked like the equivalent code.
Have you compared this to a Scala implementation of the same?
No, I haven't actually. It's a good chance that Scala would be more terse, but yeah, sorry?
In Scala, you'd have, well, you wouldn't have the parallel stuff, and you wouldn't have to collect at the
It
end.
would look a lot better.
Yeah, but I
Yes.
oh, sure, but as in, sorry, I mean, I guess the bit about the end, about the collecting step at the end, basically everything return something.
Would do type inferences for you.
Yeah, and it's doing a lot back behind the scenes there too. Back
Yeah.
grouping, that third, fourth line there, collect grouping by is doing a lot of type inference from Java as well.
Mm. Yes.
So I assume that the parallelism stops at sorted?
It actually stops at collect, because that's actually this is actually 2 sets of streams. We could make the stream parallel, but so in fact it's only the first 3 lines that are in parallel, and the last 5 lines are actually serial in this case. That's because once it's collected, it's now just a plain collection. And then I've actually created another stream here, and I could put parallel stream in there. But this is an example. I didn't test it to see which would actually be faster.
What's the 2 colon syntax there?
This one.
Yeah.
Okay, so what this does is that this is probably a better example because that's more typically what you would see, is that it says call this method for this type on each element. So it's equivalent to, say, taking x arrow x dot get key. And the reason for using that syntax is that it's actually handled a little bit more natively, and depending on the use case, it's a little bit clearer, but not always. You'll see some of the later examples where I don't do that for other reasons. But where it gets interesting is that there's a magical method called new. So if you do see type : new, it actually means call the constructor. The interesting thing is that if you have a method that, if you have something that doesn't take any arguments, like your Lambda that you have to implement doesn't take any arguments, it will call a constructor with no arguments. But if you have a Lambda that takes an argument, when you call new, it expects to call a new constructor with the argument that matched your type. So, what you don't see here is is how many arguments it gets called with. What can be even more confusing is that sometimes you don't see a type, you see an instance of an object. I think I have an example later. So, for example, say I wanted to peek at these values, I would put in, say, here, I would have peek system.out : println. So I'm actually using system.out as an argument, and the object itself gets passed into the println. So it doesn't have to be a type, it can actually be an object you're referring to. One of the things about it that I think nerves a lot of people is a lot more magic going on. Exactly what is going on is quite confusing. To give an example, this here doesn't actually create a class at compile time. There's no code, not really any code at compile time. There's no methods, there's no classes. There's more meta information, but that's it. Instead, what it does is it creates a class at runtime. So there's still a class created. You could still get that instance and call get class on it, and you would see a class name, for example. So again, more magic. Any more questions on this slide?
That double colon that's new in JDK8, is it? Okay.
Yes. It's a way of referring to a method without actually calling it. So it's a way of referring to it as a Lambda.
Right.
Sorry. Yeah?
So just on the last point, say it is generating a class at runtime, and you ask for its name. Is it named similarly to how an anonymous class would be named? You know, like blah, 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 blah?
No, it's far more cryptic, unfortunately. Yes, anonymous classes at least have the benefit that they're numbered in the order in which they compiled in the code. I'm not sure if that's a standard, but it's certainly the way the compiler does it. It's a fairly logical way of arranging them. Instead, these are numbered in the order in which the lambdas are created globally. So depending on the code paths your program runs, the same lambda can have different numbers on different runs.
Great.
Yeah, fantastic.
And how many objects of that class will be created when we are using this parallel?
It's an interesting question because it may not be the number you think. And I'll show you why a little bit later. So we've led on to a later slide. But anyway, any more questions? I'll put this up on SlideShare later. Okay. So one of the things that I see as a shift, and because I'm writing libraries that use lambdas and writing libraries for Java 8, is that conceptually, certainly up to Java 7, you would think of passing in a strategy object or an object to a library, and then the library does something with this object and then returns a result. What is different here is that, in fact, Java 8 optimizes very heavily based on inlining. Java 7 used inlining a lot, but Java 8 actually uses it even more, which means that in many ways what happens is not you passing code into a library, but the library actually comes into your code because it's being inlined, and in fact your Lambda goes nowhere in reality. In fact, it may itself be inlined, so it may end up in the calling code for the thing that called it. The reason that's significant is that a lot of the optimizations are based on this assumption. And you can and when you're writing a library, you can end up writing things which are much more like, say, macros or templates in C++. You want to create wrappers and simple methods. And an example of this is, you might write, this is a fairly common boilerplate code for handling reentrant locks in Java. So you would write out the fact you want to lock it, and then you would do something, get a result, and then finally you would have to remember to unlock it. And a lot of find bugs have got checks to make sure you do unlock it in a finally block and all that sort of stuff. But what you can do in Java 8 is you can actually say, you can write a method like this, which says, give me a lock and callable, which is a piece of work you wanted to do, which returns a result and can throw an exception. I will use this structure. But because this will get inlined, because it's so small, it will actually effectively write the code you had in the previous version for you. And all you end up doing is writing this. You say with a lock, and it will do all the locking code around it, call this method, right? And what happens after inlining is that you get the code you had in the Java 7 version, but with a lot less boilerplate, a lot less error prone. Where this is particularly useful is when you've got more than one concern. You've not only locking, you've got something else you have to worry about that needs to be cleaned up as a resource. And so it becomes a much smarter version of try with resource capability. Because try with resource has to be closable. This can be anything, right? You can write any kind of structure you want. And so you can start to take some of that repetitive code you have in your code base and start eliminating the duplicate and boilerplate, turn them into methods themselves, and expect to have them inline enough. They will be. Now, one of the things that's interesting about Java 8 is that they've also, so this is an actual example from one of our unit tests. What we have here, the purpose of this library is to create a serialization API that will handle just about any kind of format. So we want to say, we want to write an API where you don't need to know what the serialization format is, whether it's text, YAML, JSON, binary, raw format that's just pure data. It can handle anything and handle it in any order, and it will handle different schema changes, optional fields, all of that stuff is done for you. All you need to worry about is what fields you expect and what their data type should be. And you also should expect it to optimize it as efficiently as you could hand code it yourself. So it's quite ambitious. But then you would say, oh, wait a minute, I can see all these objects being created, lots of them. But in reality, what happens is that the JVM inlines all these other methods, and at this point says, well, wait a minute, I'm creating an object for this Lambda, which it doesn't escape this method. It's called escape analysis. And so I don't need to create it on the heap. I can create it on the stack. And in fact, for the Lambda, it's a Lambda with no field. So it wasn't always going to be an object which had nothing in it anyway. It was just an object of a type. So by putting it onto stack, it just disappears completely. And in fact, what happens is this code just gets inlined back into what is effectively our templating function. This has an interesting side effect because you can actually see the point at which this fails to work. So it's a little bit washed out, but in fact, one line disappears and no, it's just washed out. All right. So what the blue line is the number of bytes per call to the previous method occur based on the number of fields we had in there. So this had 8 fields. And at 8 fields, this produces, after it's warmed up the code, produces no garbage whatsoever, no objects at all, right? Add one more field, the whole thing fails and it starts going, they all produce garbage, right? Which is that's where you get this blue line. So as you add more and more fields, it just gets more and more garbage, which makes sense. But for methods that are small enough, it optimizes away completely. And these two lines, the yellow and the orange, is actually just plain throughput or average latency. So you can actually see that it does hurt even the throughput, let alone the latency. Even if you don't worry about GC pauses, it's still going to be hurting your performance. So why is this? Well, what we did here is this gray line is, what if I took all the fields I had but always put them into two methods? Right? So eventually I end up with two methods of 8, which as we saw was fine. It didn't produce any garbage. If you have just two methods of 8, it's all good. It still doesn't produce any garbage. So I was thinking, oh, you know, do we have to have some arbitrary cap on the number of fields you can do, and then it suddenly starts working? But turns out there is actually a setting for this that you can trace. You can actually say, this is the bytecode escape analysis trace level, and it produces this warning for this method when you have more fields, and it says, it warns that the number of bytes, after inlining, the number of bytes in the method is too large. And in fact, it's 271, and it exceeds the default of 150 bytes. So 150 bytes is large enough that 8 fields will get escape analysis performed on it. But if you put in a 9th field, it goes over that threshold and it just gives up and doesn't do any escape analysis. So this affects not only Lambda code, but also anything that's got anonymous inner classes as well. So even if you just take Java 7 code, put it on the Java 8 JVM, then this can actually make a difference in terms of how much garbage and the performance you get. And the way, in this case, the solution was to increase the limit to 300 bytes. And if you set the limit to 300 bytes, then in all cases, well, up to 16 now, you could, it would optimize it so that all of the Lambda objects that get created are actually eliminated. So in the previous example, to answer your previous question, apart from the parallel bit, because it has to create some objects there, they are escaping the current thread and the current method. With inlining, you may find that a lot of the objects it created, so if we go back to the very first example, this is notionally creating an optional, which then passes through to another optional, which passes through another optional. This could be creating an optional, this could be creating an optional, and finally you throw it away, which seems like a waste in terms of objects created. And in fact, this is an object, because it's a Lambda, another one, another one, another one, right? So you've got about 8 or 9 objects potentially be created here. But in reality, once this code warms up and it realizes that none of these objects go anywhere, it can put them all onto the stack instead of on the heap. And then those objects become trivial because they're all referring to values you had previously. And in fact, they'll all disappear. So you can have a method like this actually create no garbage whatsoever, which is a pretty cool feature for Java 8. Java 7 doesn't have anything like this, really. Yes?
What's the rationale behind a default of 150? Why not have it higher?
I don't really know, to be honest. I think they probably just picked a level at which they considered it to be really cheap. It also could be because compared to Java 7, they're already doing a lot more, and they sort of felt, well, we're already doing so much, why tune it even further? But I'm more inclined to just say go for broke and find a value which I would consider unacceptable to go any higher. But the reason it's particularly significant is that there's another default, which, because this is heavily dependent on inlining, there's a inlining default of 235 bytes. At less than 235 bytes, a method can still be inlined if it's called enough. Over 235 bytes, it won't be inlined. So what can happen is that depending on, because this threshold is much lower, depending on how it does the inlining, and based on sizes, it will depend on whether the escape analysis will kick in or not. So you can end up where your inlining effectively hurts your escape analysis by pushing it over this threshold, because it will go all the way up to 325. So since I've been doing this slide, you could probably set this to just over 325, because at that point, to go any higher, you probably have to increase the inlining threshold as well. So 350 is probably a better value than 300.
Is there any downside to inlining larger?
The most obvious downside is just more and more computing time. I have a feeling it's not linear, which is probably the reason why they try to put thresholds on it. But if you're trying to do work in the low latency environment, generally speaking, you want to spend more time on your warm-up on startup so that you spend less time when you're running. And so if you could, whenever you can make that trade-off, it really is worth doing. It could be that we have a fairly specific use case where we would tend to just push everything up to the limit.
So it can be said that with the Java 8, the optimization is a must for every...
If you're going to write code this way, basically in Java 7 you just didn't use this. You just didn't write code that way. You didn't create objects at all. If you're going to stick to your 1 gigabyte an hour garbage, right? On a per object basis, you wanted on average less than 1 byte of garbage, which is for the entire message, right? For end to end, from a message coming into the message going out of your system, you want on average less than 1 byte. So it's a fairly ambitious target. So you set that, and you code that way, so which is not really natural Java at all, right? And that's how you achieve it with Java 7. But the fact that Java 8 will help you with a lot of that elimination means you don't have to code it that way quite so aggressively. And then instead what you can do is you go the other way around. You write the code and then you optimize it later, which is really the pattern. It's a much better pattern. Because what you then do is you find out all the points where the JVM doesn't optimize it away for you, and then you code those. But if the JVM will do the work for you, there's probably no point you doing its job for it.
But message there is fairly cryptic. Is there a way to work out which method it's talking about?
Yes, there is. There's a line before this which says which method it's complaining about. Leave it that really. But that's the line to look for in terms of as a hint that your methods are getting too big for this kind of optimization. So I've got another note here on type inference. Now, the type inference is something that happens at compile. Oh, sorry. Before I go into this, is there any more questions? No? Okay. All right. Type inference is something that happens at compile time for the most part. And it happens in some ways which are slightly surprising. This very first line here will not compile. And the reason why it won't compile is it can't work out what type that's supposed to be. Right? It needs to know at compile time what type that will turn into. Even if you were to pass object into a runnable later, like it is on the second line, that's too late. It has to have known from that line alone what type it is. Now, in some dynamic languages, you would be able to write a lambda like that and just have it as like a generic block of code that gets compiled where at the point at which you know what you're going to do with it. You can't do that in Java. It actually has to be able to work out the type. So in fact, on this second line, what it does is it creates a runnable object. Right? It can infer from what you assign it to that it's a runnable. Now, there's something you can't do in Java 7. Java 7, there's only one real exception to do with method handles, is it never looks at what you're going to assign it to work out what that type should be. The expression on the right-hand side must be self-contained. You must be able to work out the type from the expression alone in Java 7. But in Java 8, it looks at the entire statement. And from that, it can work out not only how it's how the values are, that it refers to, but how it is used. And the last one is rather odd in the sense that this is not really a cast. Right? Now, this is actually just telling the type inference what type you expect it to be. So it looks like a cast, it's syntactically like a cast, but in reality there's no runtime casting going on here. It will actually, at compile time, create an object which is basically the same as this, except that it actually implements two interfaces instead of one. Now, the interesting thing about this one is that this one is actually serializable. That one is not serializable by default. Lambdas are not serializable by default. There are ways of fiddling with that, and so if you want a lambda to be serializable, you have to implicitly cast it to a type which it is itself serializable. And then at runtime, when it generates the code, it actually has this little check. You can have a look in the Lambda, meta Lambda factory. It has a little check to see whether the interface it needs to generate for is serializable, and actually adds in a write and read object method for those types. And this is actually used by the JJOQ library. What it does is to work out what a lambda does at runtime, it serializes it to a dummy object output stream, and then captures the information it tries to write to work out what the lambda does, which is interesting.
What was it that does that?
Sorry, JJOQ. JOOQ.
Yep.
Sorry.
I've
Yes.
seen it. Yep.
Yeah. In case you're interested, JOOQ, I'll blame the jet lag. Anyway, JOOQ is a library that will, you write Lambda code and it will convert that into SQL for you so that you can point it at a JDBC connection and manipulate it as if you were doing Lambdas, but in reality it turns it all into SQL and then talks to a database for you instead. So, which is quite cool. But it has to do quite a lot of sneaky things under the bonnet to be able to turn your Lambda expression into the equivalent SQL code to do the same thing.
So with those first two, so I understand that when you're creating a lambda, the JVM has to look for a functional interface that matches the parameter list and matches the return type.
Yep.
So in that second one, it can find, it says, well, runnable matches no parameters and return type of void. But the first one, it's simply saying, I don't have a functional interface of type object.
Correct. Yes. One of the things I found confusing initially is there is an annotation called functional interface, and all of the functional interfaces in the JDK have this on it. Yeah. So then I wondered what happens if you don't put it on it. And essentially all it does, the functional interface annotation does, is it's a compile time check for an interface to say this is a valid functional interface. So if you it's like override. If you put it on an interface which is not a valid functional interface, that interface alone will fail. But if you don't put functional interface on, it can still work. You just don't know until you use it, basically, whether it's going to work
So
or not.
it'll still look through all interfaces, even if they're not marked as functional interface.
Correct. They don't have to be marked as functional. You can take an interface from Java 7, Java 1, and as long as it has only one abstract method or only one method that's not implemented, this doesn't work for abstract classes, just interfaces, then it can apply. And so that interface, that missing interface method can actually come through a whole directory tree of marker interfaces and so on, or a whole tree of classes. The interesting thing is, the reason why I say this is that in Java 7 you can also put default methods and static methods on your interfaces. And in fact, in our libraries we use that more heavily now than Lambdas itself. So that's actually a very useful feature for writing libraries, is putting default methods on interfaces, which gives you something a bit like multiple inheritance without multiple fields. You can't have multiple inheritance for fields, but you can have multiple inheritance for implementations. Yeah, exactly.
In Java 8.
In Java 8, yes. So you can add a default method. So you can have a marker interface, a functional interface which just has one unimplemented method, and then multiple methods which are implemented because they've provided defaults. And this is all on the interface. I think I may have mentioned a lot of these things already. Just a reminder, so notionally there's no class, right? So from a high-level view, you should imagine that there's no real class associated with the Lambda, but in reality, at runtime, there is such a class. They're lighting up the fires. So you do still get a get class, right? It's not as useful as you might imagine, and apparently Brian Goetz replied to one of my questions on Stack Overflow and said, this is quite deliberate. It's to stop you using it for something that they never intended. Although we got some plans to write a library that will make it useful. The other thing is when you have some actual code, so these ones are method references. These are done entirely through metadata. But these ones are not. This actually has a piece of code. And this piece of code actually sits in a static method. So what this would look like in the bytecode level is it's a method reference to this static piece of code, a static method that was generated. All right, so you end up with generated extra methods, not extra classes. There's for constructors, there's class new, and the other thing to think about is that this will use heavy inlining. They use inlining extensively, far more than in Java 7 did. So don't necessarily think about the fact that you're passing through an object, but also think about the fact that after all of this is inlined, it's going to act more like a template. And in fact, if you ever get a crash dump of one of these things, it's quite confusing because, in fact, so many of the top levels of the stack all disappear. So when you do a crash dump, if you ever crash out a JVM and do a .h prop file, I can't remember the name. Anyway, if you ever crash out your JVM, it'll give you a stack trace, but it'll only give you a stack trace of the actual methods, not before inlining. So you can actually see how far into your code has disappeared. And for a lot of our libraries, because we try to be low latency and very terse, they often disappear entirely. Because some of our stuff is so level, we do create stack crashes. And, but unfortunately, you don't even see them because it says that our code isn't. It's the caller's code that seems to be to blame. So yes, assume that there's going to be a lot of inlining. And yes, so one little last note. Let's see if we can figure out what that will do.
Exit 128 times.
Well, it can only do it once. But your exit code becomes somewhat random and entirely system dependent. Okay. I think we've all had enough, but is there any last questions before we take a break?
Why did you, what was the requirement to change from C# to Java?
Yes, okay, so this is one of the most common questions I get. So it makes it interesting. There was a number of reasons, partly organizational. The company was being merged with a parent company and they were a Java shop. But there were other benefits, and probably the main benefit of Java over C#, having worked on both of them, is that C# integrates very well with SQL Server, which means that your code becomes incredibly tangled, especially over a long period of time. It's very difficult to figure out what the interaction is backwards and forwards between your C# code and your SQL. And in their case, we took a very long time to even figure out what tables were involved. 6 months, in fact, of investigation, just to untangle it to the point where we actually had a complete list of tables involved in this program. Right? Whereas in Java, it's not as friendly, but that actually worked for us in the sense that it gave us a very clear distinction between the database and the application. And that meant we could make the interaction between the database and the application much more efficient. And in our case, we improved the performance, the amount of processing power needed by a factor of 10 to do the same amount of work. And a lot of that was actually down to, not because Java is more efficient than C#, although there were some improvements there. Most of it was actually about making a clear separation between what was done in the database and what was done in the application. Sorry, yeah?
Do you know if there are any plans to get Java, get hints into the code that, so I write some code that I expect to be inline, and if it isn't, then my code's not going to be running as fast as I want it to. So
Yes.
maybe an annotation on my code, so get the compiler or the JVM to
Yes.
fail.
Yeah, there is actually an annotation in Java 8 called force inline, which sort of is down that road. It's not widely publicized, and I think part of the reason is that at the moment it's a bit of a hack, and in the sense that the intention is always to be that you should never really need to do that. It's just there because for internal purposes it makes it easier for them. But there's also one that does the opposite. So method is never inlined. So I think the general view is that a lot of tricks in terms of optimizing the JVM have an average lifetime of about 7 years, right? And a lot of code will outlive that. So in fact, you may find yourself optimizing for things which further down the line no longer apply. One good example of that is the use of conditional move in Java 8. So there's a number of tricks. So if you've got a question mark colon, like max, for example, max and min, that used to be a branch in earlier versions of Java. It had to do a branch. So it said if condition, then it was A, otherwise it was B. Now in Java 8, that is optimized away as a conditional move, which means that it takes two values, and based on a flag, it will take one value or the other. But there's no branching going on. So now your branch misses and all of the stuff that you used to need to worry about disappears. You don't, So what happens is that over time, and to some degree it's some of the object creation, some of the optimizations which made a lot of sense before no longer really apply. One of the common myths was replacing string buffer with string builder. I still see people use string builder today. In fact, I still see people use string buffer, but that's another story. It's only been 10 years since it's been replaced. But anyway, so there was this view that if you use string builder, it will be more efficient than just letting the compiler do whatever it does. But in reality, what the compiler does is it uses string builder. And in fact, you can end up, if you hand write it yourself, you can end up writing less efficient code than if you just didn't try and do that in the first place. And you've gone to a lot more effort and written a more obscure code. String builder helps if you've got some sort of loop. You're looping around and you're building up a string. But if you've just got a single expression, like most two strings, the way they work, the code will be as efficient as you can write it in general, just by doing plus, 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 plus all the way through. So yeah, there is an annotation that does this. You probably don't want to be using it, is my answer. And it may well disappear in a future version because it's kind of a hack.